So thank you for the kind introduction. As already mentioned, my name is Maximilian Brodbeck. I'm working under the supervision of Professor Tim Ricken at the University of Stuttgart, and will today present some of our joint work with Professor Florian Bertrand from the University of Chemnitz on a posteriori error estimation. So, well, just as a very brief motivation, let's consider a classical footing problem from poor elasticity, so a rectangular domain with some distributed loading on top. Well, of course, we could solve something like that with a uniform mesh, but something that looks probably somehow like this. So with refinement where things are happening is probably more suitable. A classical procedure for that is we solve a primal problem, we estimate the error in some way, we mark our mesh and refine it then. Well, that's quite standard. The question is just, well, how can we estimate the error? And if we're talking about these equilibration-based error estimates, well, we construct our error estimate based on our primal solution, plus two additional terms, what we call an equilibrated flux, so an equilibrated stress tensor, and an equilibrated seepage velocity. For the engineers, well, this is in some ways related to a classical Sienkiewicz-2 estimator, so we have an improved flux and we compare it to the primal flux, and that's the basic idea. Our main problem with that, well, we couldn't find a library where we can where this reconstruction processes were implemented in an, let's say, efficient way. So this is what we did, and this is what I want to talk about today. But before we go into the details, probably just a short idea what's the difference between the flux and our equilibrated fluxes. So we take conservation law in divergence form. Shortly, so we have the divergence of a flux is equal to some right-hand side. We solved that in a weak formulation, so we've got our primal variable somehow in let's say H1, and if we take the gradient, the symmetric gradient, or whatever we need for our fluxes, well, the flux is in L2, so it's discontinuous over the cell boundaries, and this is probably not how it should be. So the basic idea is, well, the natural space for fluxes is probably or could be H-diff. So well, we want to say the divergence of something is equal to something else, so H-diff seems to be fine, and also, well, the flux is then continuous over our element edges, and this is what we would like to have. So the basic question that we are asking in equilibration is, can we find an equilibrated flux in H-diff such that it is close to the flux that we calculated from our primal method, and that's what we want to do. Of course, we could now simply project L2 to H-diff under some side constraints, but this is too expensive. So we think about, let's say a localized procedure. So we build up our reconstructed flux from patchwise solutions, and on each patch, we are simply solving a constraint minimization problem. So the reconstructed flux is close to the localized primal, so flux from the primal variables. Phi is nothing else than a head function, which is 1 at the patch central node and 0 everywhere else. And well, the flux has to be in some H-diff space, so we consider some boundary conditions here. And it has to fulfill, let's say the conservation property, but this F is a projection of the actual F into some polynomial space. So we now either solve this problem by a simple constraint minimization problem, but we would like to avoid that because these constraint minimization problem, even on the patch level, can get quite large and therefore a bit expensive. So what we would like to do is do that in a semi-explicit way. So we slightly modify our solution on each patch. We take, once again, the localized flux from our primal variables and add two corrector terms. The first one, which is the one with the tilde on top, is simply any function in H-diff that fulfills our divergence condition. And this is, let's say, something like an interpolation to find such a solution. Main problem, well, we do not use all degrees of freedom on our patchwise H-diff space, so we will not fulfill the minimization problem above. So we have an idea what a solution looks like, but that's not all. And then we need, then we have some part of our minimization problem, and then we simply solve, then we have a second corrector, well, including that one into the minimization problem on top, and considering the fact that we have solved the minimization not on H-diffs, but we're using a so-called patchwise H-diff 0 space, so an H-diff space that has a 0 divergence on the patch. Then we end up with an unconstrained minimization problem, and if we add that up, well, we have fulfilled our minimization problem, and when we have found our reconstructed flux.
So nice in theory. Two things that we require for that. Well, we have to build up this patchwise HDiff0 space. So we required what we call an hierarchic definition of the Ravier-Thomas space. So a clear separation from the degrees of freedom on each element that alter the divergence, and those who simply don't do that. So we implement that in basics. Well, we currently use the Python interface because we struggled a bit with the C++ interface, but it works. And we need, let's say a non-standard assembler, because this patchwise HDiff0 space has no element-wise support. The support is on the entire patch, so we have to deal with that. But it's possible, at least in 2D. Not sure what happens when we go to 3D, but we should be able to achieve that. So we have two algorithms at hand. We have implemented both. So the constrained version by Ernen Voralik and the semi-explicit one. So basic questions: how do these algorithms perform? Well, the answer is quite expectable. We will see later that the Ernen Voralik algorithm will perform better. But before we talk about the performance, we will talk about the implementation. So what I assume now is that we have solved some primal problem with finite elements. We have defined our reconstructed flux, so an HDiff solution, which is a classical function as it is implemented in FEniCSx. We have projected our flux from our primal variables into an appropriate discontinuous Galerkin space. Again, it's a function, and we have done the same with our right-hand sides. And then, we simply construct what we call a patch. That is simply, let's say, a submesh, respectively a subfunction space. But then we loop over all nodes of our mesh, recreate this patch, recreate the DOF map on this patch, and then solve the equilibration. On the patch level, our algorithm is mainly based on a loop over different right-hand sides. So this might be a bit confusing at the beginning, but if we think, for example, about polar elasticity, well, we have a stress tensor. A stress tensor in 2D has two rows, and we have the C-page velocity or velocity field that we have to reconstruct. So we have three problems, three fluxes that we want to equilibrate in the same Ravier-Thomas space, ideally. But so we have different right-hand sides, but the same, let's say, minimization problem. So we want to make use of that. So that's why we have the loop here. If we're now in the semi-explicit algorithm, we have to do the first corrector steps. So find this HDiff function that fulfills our divergence. So a loop over different cells, and then mainly an interpolation operation. Probably we abused the interpolation matrices from basics a bit because we did some things here, but so quite basic stuff, and then the constrained, respectively, the unconstrained minimization problem. So if we are on the first right-hand side, we assemble our system or our system matrix and the left-hand side simultaneously. Use eigen to factorize that system matrix, either with a Koleski or a Luty composition, depending if it's constrained or unconstrained minimization, and then solve the system. For all other right-hand sides, besides the boundary, there we have to do some things differently. But for all the right-hand sides, we have the assembled matrix, we have the factorized matrix, we simply have to solve an equation system, and that's it. One thing that I've neglected here is that if we're talking about stresses, there's one thing wrong with this algorithm. Well, we equilibrated the two rows of the stress tensor independently, so there's no symmetry in it. So we messed up the symmetry, so we need an additional corrector here. Well, we do that weakly because we do not want to deal with Arnold Winter spaces or something similar. So we simply zero test the symmetry condition against an P1 space. We have implemented it. I won't go into detail because it would take a bit too much time. So now the promised comparison of our two algorithms. Let's consider two patches, so internal patches, so no boundary conditions involved, with 4 respectively 8 cells, and 1 respectively 3 right-hand sides, because the 3 right-hand sides, because this is what we need for polar elasticity. Let's start with the 1 right-hand side. What we see here is that that the equilibration algorithm, the semi-explicit version, is definitely outperforming the Ernen Voralik algorithm, because the equation system is much smaller. We have somehow a factor of 8 at Ravier-Thomas degree of order 4. So this is quite something. If we go to the 3 right-hand sides, well, it's not that good because main drawback of the semi-explicit algorithm, we pay the price for the reduced equation system by finding this HDiff function, and this is nothing that we can there's no speed up for different right-hand sides. We simply have to do that. So that's why in that case, the n-Voralik algorithm, where we have only the factorization of this large equation system once, performs a bit better. But if we compare cases with an k greater or equal to 2, and we need at least a Raviato mass degree of 2 for the stress equilibration, we have a speed up on these patches with 8 elements of at least a factor of 2, which is quite something. Short side note on the performance of the algorithm of the equilibration algorithms with respect to the patch degrees of freedom. We see that the n-Voralik algorithm has a scaling with something between 1.7 and 2 point something. So we see the scaling of the LU decomposition, while the semi-explicit algorithm, where we technically have shrinked the spaces on which we perform the minimization. So we have to, where we are dealing with these equation solvers, we have a near linear performance, at least up to an equilibration order of 3. So yeah, nice to have. But well, it's not. But the basic question that we ask is not which algorithm is performing better. Well, equilibration is a post-processing technique that we use for error estimation, so it should be cheap compared to the primal solution process. Unfortunately, equilibration is, well, it's no free lunch. If we compare elasticity and the BO problem, we solve elasticity with a conjugated gradient solver and an algebraic multigrid preconditioner. This is a calculation on one processor, no parallel processing or no parallel computations here involved. We see that the equilibration takes, if we take the lowest order case that is possible, somehow between 20 and 30% of the primal solution time. It's a bit lesser for the BO case, but we only use LU decomposition there. It's between 10 and 25%. But if we consider the parallel thing here, the scaling for this equilibration algorithms is nearly ideal, because there's no additional communication or would be involved if we use one layer of ghost cells in the communication. But this is So in order to wrap up, because I think I'm nearly at the end of time, we have implemented 2 equilibration strategies. The semi-explicit version is, as we have expected, that the more efficient one. We have also the stress equilibration with that weak symmetry condition at hand. So now we have the estimates based on these equilibrated fluxes were the motivation why we implemented that. So we're now in a position that we can apply that to Poisson linear elasticity or a BO problem, or respectively related problems. What's open? Okay, we're currently working on the estimate for the BO problem. Well, we have something for the space at hand, but we want to extend that to time. The nonlinear terms are also currently a bit a thing of what we are working on, and on the algorithmic side, well, we have to deal with the latest version of Phoenix. We have started with 060, and I haven't tried to port it yet, so this is what we have to do in the future. Well, there's bit of a thing with the general meshes. Reversed edges are a bit of a problem, so we haven't included that in the algorithm, but it shouldn't be a problem. And probably we can speed up the n-Voralik algorithm by using a Schur complement for the equation solver. And with that, I would like to thank you, and I'm happy to answer your question.